Now the next application is apply this to find a second solution for the series solution, and that becomes more complicated. And we'll just point out the general result because there's not many general results. You can go. You just do it situation by situation. Once you get the say you have a ODE, then you first find a series solution y sub 1, right? Y sub 1 here, and P, assuming it's a nice function, say like a polynomial or power series, at least a power series of that. And the X1 is a series solution. It doesn't have to be integer power series because of the S parameter. If S is not the integer, then it's not the integer power series. But anyway, you can still do that. You can just plug in a series solution here and here. And now you right away see the complication because you need to square the power series and then invert that. I mean, it's doable, generally doable. Inverting a series usually is an infinite series. But still you can, with some patience, you can invert that all these series, and then this P, even if a P is a power series, integer power series, this still require you take the integral of that one and then take the exponential, which again you can result in another power series, which is straightforward, but it will be a complicated mess. But at least you can do that. But we want to just discuss the general situation. Of course, if sometimes you don't have to use that. The situation when you need that is like the Bessel equation, when the first equation and second equation is linear dependent, which is when the n is integer. Then to get that, one way to get that is you use this formula. And then after you plug in that, the general situation is that when you do an integration like that, there will be a 1 over x term in here. All these power series will have a 1 over x term. And in that case, it will be 1 over x pi term. Right? When you did all this series expansion, one term with that, other term will be x pi to the certain other power. All those terms will give you just other power because you integrate over x, the power x to a certain power, and integrate that will give you another x to a certain power, except when it's 1 over x pi. If this is a 1 over x term over here, then you do the integration, what we get? Log way. You integrate that, will give you a log. I mean, integrate over x will give you log x. Right? And that will be generally the case. So all this will have a log x term in here, and then the rest will be power series of x, right? And then multiply by the original power series solution y sub 1. Okay, so that would be a general feature, general situation for the second solution, and right, and so without actually doing all this complicated invert of the power series, we can do it the other way. So once we identify that the form of the second solution is, we can now use that and plug in the equation and see what we can get. Say if you have we already have a y sub 1. We want to have y sub 2 x. That is generally is a proportion y sub 1 x, and then there can be a log x term generally, and then another term that most likely is power series of x. Right? They give it another name, so y w. Right, and So that is the form, general form after you do the integration without actually consider how you invert all this series or do this exponential function expansion. And we just assume this form and then plug it back to this equation and see what happens. So, take the derivative, y2 prime will be, there will be two terms. One is y1 prime, and then you have log x plus w. Right. The second one is y1. And then the derivative over this one is then over x plus w prime. Right. And then y2 double prime is now becomes three terms, y1 double prime log x plus w. And then take the derivative over that, which is this one. And then for the derivative of the second term, you have y1 prime and multiplied by the same factor. So altogether, you have two y1 prime. And finally, just the derivative over that one minus 1 over x squared. Right. Yeah, all this derivative, and you want to substitute the y2 prime and y2 double prime, y2 prime, y2 into here. Right. So basically, you want y2 double prime plus p, y2 prime plus q. And what you get is first, you all this term, this term, this term, you combine to just y1 double prime plus p y1 prime plus y1 multiplied by the same factor. Right? Let's combine this one and this one multiplied by p and this one multiplied by q. All three combined to this. But this one satisfies the original equation, so that is 0. Right? And the rest is this one and that one, so yeah. Okay, and then p plus this one. And you want to set that to 0. Right? So assuming this form, you can now divide this equation. This first term is 0. So now what you see is a differential equation for W. Now it's a linearly differential equation. You have a W prime and W double prime. And the rest are supposedly known. So you have y1 here, you have p is also given function. It doesn't actually depend on the q now after do that. And then y1 double prime. So that's a differential equation for W. But that's inhomogeneous. You have inhomogeneous term, which if you group W prime and W prime on the left-hand side, then the right-hand side will be something left as the inhomogeneous term. But that doesn't have a W, right? And now you can see that it's a first order differential equation for W prime, right? If you choose W prime as your function, it's only involve one derivative. And now it's the standard form linearly first order ODE for W prime with inhomogeneous term. Then you can plug in that formula and get in that integration. That most likely will give you something similar. Because this is how we did that. And again, you can do that. One way to do that is going back to the solving differential equation of first order ODE. And you do that, and except that now, supposedly this one would not have the log x term. This should be just a power series. And another way to do it is just you can find a series solution using the general method that we do. Say you have W prime over here, whatever the coefficient y1, you divide over the whole equation, then you get a solution, an equation for W prime similar to this one. and you use your standard way to find a series solution of W, and that is doable. And somewhere along the line, you see that you can convince yourself that W should be just a power series with integer or integer power. Okay, but that is another way to do it. So generally, again, you can find the second solution with the first solution multiplied by a factor that is log x plus a power series of x. Okay, so that without doing any specific calculation, the textbook did have some calculations using the j sub 0 and then solving j sub 1, the second solution of j sub 0 and j sub 1, which you get what we call the Neumann function. But this is not the standard way of defining Neumann function. In the chapter of the Bessel function, we'll define Neumann function the other way around. But you can get the general singular formula of Neumann function, which would usually call y. Some people call n, but this is y sub n. This y sub n for integer order will have this log factor near the origin. But again, we won't go through that all this calculation. It's just matching power series and or doing this integral and inverting the order of this series, which I mean it's straightforward, but tedious to actually go through all the steps is pretty tedious, and you can see that inverting series is not some. I mean it's doable, but it's take some time, right? All right.